you that's a sample. This is a sample. This is a sample. Measure the signal and every sample you have. Yeah, these are the terminology we use for the signal. You still have 2 minutes to take a break, okay? You have 10 minutes break. So, currently it's 11, so you still have 2 minutes to take. Your note is for your own reference, so you don't have to write it in a very neat way, okay? It's whatever, write whatever the way you want, okay? So long as you can read it, so long as it helps you, all right? All right, so let's resume the lecture. So we start from a continuous signal. Continuous signal. Right? X of t. And then we take a sample at every t seconds. I'm sorry, t sub s seconds. So we have discrete signal. And for notational convenience, we use x of n to replace x of n times ts. Okay, but under one condition. You and me, we know what the sampling time ts is. Okay? So that's a very crucial point. Now let's see what happens. For this figure, the frequency I think is 1 hertz. Yeah. This signal, the frequency is 1 hertz. Okay? Now if you look at the upper figure, the one above the this upper part. So here we take sample at every 0.1 second, I think. So we have those discrete signals. So this signal looks very similar to the original continuous signal. So you can see that if you connect those points, it resembles the continuous signal, right? Quite well. Okay? But what will happen if we take a sample at 1 second? Every 1 second. So every 1 second, we take one sample. Now, if you try to connect those discrete signals, you will see it is a straight line. Okay? And this straight line does not resemble the original continuous signal at all. Am I right? They are quite different. This is a straight line. And this guy is a sinusoidal wave. It's a wave. What happened? What happened? This is a very famous phenomenon in sampling theory. It's called alias. It's called alias. So if your sampling time is too big, you are going to lose information. There are lots of papers talking about this, lots of books talking about this, alias. We will see. It's called alias. Alias. Okay, alias. There's a theory. It's called sampling theory. Okay, invented by someone, mathematician. Okay, we will go through that later in another chapter. But here, I just want to tell you, whenever you are considering design a discrete system, the sampling time is very important because if your sampling time is too big, you are going to encounter the alias problem. You are going to lose information. This is a disaster. Okay? So it is extremely important. Alias problem is an extremely important. Alright? So we are going to see that later. It's called sampling theory. But there's another name for that. Okay? So the one who discovered that theory. Now, if the sampling time is Ts, okay, Ts second, then 1 over Ts is called the sampling frequency. Fs is called the sampling frequency. Sampling frequency equals 1 over Ts. Again, Ts is the sampling time, or sampling period. Okay. That's the terminology we are going to use a lot in this course. Okay, this is a figure of stock market of imaginary companies. Okay, let's skip this one for the moment. Move to this one. Now, in this course, the name is signals and systems, right? In the previous few slides, we were considering signals. But now let's move to a very simple system. Very simple system. So let me give you a very brief introduction to the system. Well, I think most of you have learned the differential equations, or ordinary differential equations, right? Okay, most of you. Have you taken a course? Differential equations? No, not yet? Really? Okay. But here, I think most of you have learned the differential equations. Okay, anyway. So presumably you have learned, okay? If you have questions, come to me after the class. Alright? Okay, so let's look at the differential equation given by the lecture notes on this left. Okay. Vi divided In the previous slide, I asked you to write down the closed loop structure. Now, if we consider only continuous time signal or continuous time point, so we have a point over here. We have a controller over here. Okay, now this one, usually that's a system you want to control, to be controlled. It can be an aircraft, can be an engine, can be a whatever the circuit, okay? Can be a CD player, whatever. Now this is the controller, okay? Can be a PID controller, can be any kind of controller. For simplicity, let's ignore the controller. So let's replace this by one. Just for simplicity. So it's a very simple controller. For unity controller, we don't need to connect it to the plastic. Now, the way we describe quant, the way we use to describe the quant is to use differential equations, because for more than I think 95% of the system in the nature, they all belong to the continuous system. Okay? Only a few percentage of the quant or the system can be categorized as discrete system. So in order to describe a continuous system, we use ordinary differential equation, right? X dot. That's a typical, that's a very general way to describe the system. Okay? But then, for linear system, we write it in this way, X dot plus D. Okay? But this is in tandem. And then we also can use I need a help. I call this CSI, GOS. Okay, this is in S domain or frequency domain. Okay, we will see that in detail later on. I'll just give you a very brief introduction at the beginning, okay? So, if we go back to the slide, here we have a very simple differential equation. Vi of P equals to Vc P is bigger than or equals to 0. Okay? Now, if you look at this equation, it's a first order differential equation, right? This is the first order. here we have one differentiation only. So that's why it's first order. Now this is a differential equation with the input. So this guy plays a role of input. Okay? And this piece of C plays a role of Y output. So Y is the output. Okay? X is the state. U is the input. Again, we will go through this again later in the class, so don't worry about that, okay? Because this looks weird in the beginning for everyone, okay? But don't worry, like I said, I just want to give you a brief introduction first, okay? All right, now, in a node, we have a differential equation like this. It's a first order differential equation, and actually this is used to describe an RC circuit. It's an equation for the circuit, okay? So how do we interpret this equation in the system way that we are going to learn? So we have U, we have a signal U, okay? We have output Y, and then we have a state variable inside of 1. The state variable inside of 1 is denoted by X. Got it? Okay. So we have a U, which is the VI. And we have the output, which is called VC. Now this means it's a subtraction. Okay? Let me give you a little bit few words here. This minus sign here means it's a subtraction. Okay, and we call this error signal. So by definition, so I use a minus sign here, positive sign here. This So this is a very simple closed loop structure. It's a very simple closed loop structure. Okay, forget about this for a moment. Let's consider this. This is quite similar to this one, almost identical in structure. So we have an input U, we have an output Y. Okay, this guy's U, and this guy's Y. For a differential equation, VI minus VC equals differentiation of VC. So I have VI minus VC. This is VC, so I took the signal from VC and then send it to the addition. This is actually a subtraction. Okay? The addition. Okay? VI minus. So this is VI minus VC. And then equals to the differentiation of VC. This is VC, and this is the differentiation of VC. So which means there's an integrator. Right? Because the output is VC, and the input to this operator is the differentiation of VC. So which implies this operator is an integration. This is an integration. Any question? So this is VC dot. If you integrate VC dot, that gives you VC, right? Integrate VC equals VC. Okay? Got it? Okay, so that is the first way to interpret the differential equation. I have another one to interpret the same differential equation. Now this time we write it as d minus the differentiation of VC equals to VC. The same, right? Okay, they are the same. Can you hear Taiwanese? No? No? Not yet? Try to learn it. Okay, anyway. So we have the second interpretation here. So how do I transform this equation into the schematic diagram like this? Okay, so I have a VI, again, that's the input. And then fit it to the addition operator. Oops. But this guy, we subtract the differentiation of VC. So here I have a differentiation operator, DODT. And then equals VC. Now, at the first glance, you will see that, well, they look quite different. Here we use integrator. This is an integrator. Okay, in the second loop, we use differentiator. This is a differentiator. They are quite different, right? But I will tell you, mathematically, actually, they are the same. Why? Now, this is in the time domain. Okay? But if I use S domain, I assume you have taken a course and you have learned Laplace transform. But we will go through that again, okay? Don't worry. So let me assume you all have taken a course and you learn the Laplace transform before coming to a class. Okay, I assume. So let's use the Laplace transform. In the S domain, integrators you notify one over S. So let me use the okay. Differentiation is simply S only. So S in S domain means differentiator. 1 over S in S domain means integrator. Okay? And then let's consider this equation. Let me use equation star to denote this equation. So equation star. Let me repeat that here. So now we're going to play a trick. Here is the magician. Here's the magic. Okay, I'm going to take Laplace over the entire differential equation. Okay, so this means Laplace operator. So I have Laplace operator of VR equals Laplace operator of VC plus the Laplace operator transform the differential equation to S domain. So the first term is equal to, let me call this Vn of S. Okay, let me call this Vn of S. It's simply a notation for simplicity. And then the first term on the right hand side is Vc of S in S domain. Be careful. And then what about the second term? It is a differentiation of a signal Vc. So it's multiplied by S times Vs. Okay, one more time, we denote the Laplace transform of Vi by Vi of S. We take the Laplace transform of Vc of t, it becomes Vc of S. This is simply a notation. Okay, so Vc of S is the Laplace transform of Vc of t. The Laplace transform of the differentiation of Vc of t becomes S times Vc of S. Now this is a property of Laplace transform. For this moment, for the time being, I'm not going to prove it. So assume you can take it. Okay, assume you can take it. So we have Vi of S equals Vc of S plus S times Vc of S. Okay? Okay, so the right hand side can be simplified. Vi of S equals 1 plus S times Vc of S over Vc of S equals to 1 over 1 plus S times V of S. And this 1 over 1 plus S is the G of S, the transfer function of the system. Okay, so if we use the Laplace transform, we can end up with the transfer function for the system. Now let's go back to the previous procedures here, and take a look. Are they different or are they the same? Okay, now again, let's take Laplace transform over the entire system. Over the entire system, okay? So here we have, this is, this becomes the Vi of S. Use the notation we have defined before. And this is Vc of S. Okay, so this is Vi of S. And this is the Vc of S. Okay? All right, so I have okay, let me call this error signal just for convenience. E of t. Okay, so after taking the Laplace transform, this is E of S. Right. So let's look at this structure here. So I have Vi of S minus Vc of S. Okay? Equals E of S, the error signal. Now the error signal goes through the integrator, that is times 1 over S. This guy times this one. That's equal to Vc of S. So I can combine these two equations. So from the second equation, E of S equals to S times VC of S. Okay? So I can replace E of S by S times VC of S, which means the differentiation of VC. Okay? Alright, so then put it back to the first equation. I have VI minus VC equals S times VC of S. So we can see that we have the same thing here. So I just move the VC to the right hand side. So we have VI equals to VC 1 plus S times VC. Or VC equals to 1 over 1 plus S times VI. The same as this one. Right? What about the second one? Okay, I leave this to you. Try to convince yourself. If you use this structure, you end up with the same conclusion. Okay? So I leave this to you. Please do this by yourself. Okay? Got it? Alright, try it. Try it. So I don't want to do everything. I leave part of this to you. And you will see that when they are all identical, they are all identical. Okay? Any question up to this moment? Yeah. Sorry, say that again? Oh, this means it's. You mean this one? Well, that's a notation for the addition operator. This is an operator addition. We add the signal. Okay. And then you erase it. This is a typical symbol for addition in automatic control. Okay? So this is plus, this is minus. So have a signal in this case. Both VI and the VC, they are the input to the operator. This is an operator addition. Okay? So here we have two inputs, VI and so to the operator. To this operator. Okay, not the input to the system, okay? But to the operator. And this is the output. So there is B of P to know the output. So this is the output of the operator. So by definition, okay, it's a common definition. The output is equal to the input VI minus VC. That is because I put a minus sign here. So this minus goes to here. Okay? So this minus sign goes to here. And this plus, positive sign, positive sign in front of VI. Okay? So alternatively, if you see a notation, let me do this. Both of them are positive. It is very likely. Okay, positive feedback. This is VI, suppose this is VI again. And this is also VC for some reason. This is E. Now here we replace the sign, the minus sign by positive sign. Then the error signal, ET, becomes the sum of the two input signal, VI of T plus DC of T. It is purely a definition. Okay? So one more time, this positive sign go to here. Go to here. And this positive sign go to here. Got it? It is only a sign convention, just a definition, to simplify the operator's notation. That's it. Okay? So be careful when you are reading a paper. Sometimes the author will make a mistake on the sign. Okay, be careful. It is a huge difference between the sign. Okay, it is a huge difference. If the system has a stable negative feedback, then that's fine. If you replace the negative feedback by the positive feedback, you will usually you will destabilize the system. That's a disaster. Okay, we will see that later on. Okay. All right. Any question up to this moment for this part? Okay. All right. If there's no question, then let's move on to the next topic. Right. Okay, next topic is about a complex variable, a complex number. How many of you in this room now has taken a course about complex number? Would you raise your hand? Have you ever taken a course, mathematics, and your teacher or your professor taught you or tells you about a complex variable or complex number like this? Complex number, complex variable. X plus I times Y? No? Are you serious? Yeah, in high school, yes. Back to the high school, yes. Yeah, okay. Gentlemen? No idea. You don't remember? Well, okay. Okay? A lady? Yeah, okay. All right, so learn the complex variable or complex number long time ago, but for some reason he or she forgot. Okay? Okay, that's fine. Let me go through this very quickly. Okay, have a quick review on the complex number or complex variable. Now, due to the time limitation, I won't be able to go through every details. Okay, so forgive me. So I can only give you a 33. Introduction and review of the complex numbers. Okay? Complex number is a very convenient tool to express signals, so that's why we have to learn how to use complex numbers in the beginning. And actually, for a two-dimensional vector, it is to a complex number in some sense. So suppose I have a Cartesian coordinate, x and y coordinate, okay? And then there is a point. There's a particle. Okay? If you have learned dynamics, you can imagine that it's a particle. Sorry. In the physics or dynamics, how do I specify the position of a particle? We coordinate x and y, right? Okay? But then let's imagine that this can be expressed. That's a vector. So I and J are the so that's a vector. That is a vector, two-dimensional vector. But for a complex number, which is very similar, so let me leave that here. Okay? And then now this time we have a complex plan. We have a real axis. We have an imaginary axis. Looks like. Usually we use the x to denote the component along the real axis, and y or something else to denote the imaginary part of the complex number. And likewise, we can have a variable complex number. Let me call this D. Yeah, that's D. Suppose the real axis or real component is x. So how do I express this complex number on the complex plan? We use x plus I times y. Or j times y. Okay, sometimes we use j, sometimes we use I. But let me use j. Okay, because then the variable I can be confused with the current. Okay, so let me use j instead. So the V is equal to x times y. J times y. So where the J means the square root of lambda. Now this is a great invention by a mathematician. I forgot his name. Okay, that's a great invention. And x, that's a real part of D. This is the real part of the complex number Z. And a y, that is the imaginary part. The imaginary part. Okay, so that's the definition of a complex number on or in the complex plan. So Z is the complex plan. This guy. This is the complex. Very similar to a Cartesian coordinate. Very similar. And there's another expression for this complex number. Now look at this complex number. It has an argument. Okay, this argument theta is the angle between z and positive real axis. Okay, and also we can calculate or determine the distance between the origin. Okay, here's the origin. Yeah. Between the origin and the complex number. So let me use R. Very similar to this location. Right? Very similar. So I also can write it as R times e to the theta. Wow. That's a remarkable notation. Okay? This R, that's a magnitude, that's equal to the square of x squared plus y squared. So that's the magnitude or distance between the origin and z, the tip of the z. And theta is called the argument. Okay? Arctangent of y over x. But sometimes we prefer to use the location arctangent 2. And that's fine. In a computer program. Okay, but this is a typical definition. This is the base or argument. Of the complex number z. So from this notation and this geometry, you can see that I can put in r times cosine theta, j times sine. Right? If you look at the geometry, okay, and which means so let me repeat that here one more time. So r times e to the j theta. And this real part is indeed the x dx. So this line is the x. This line is the y. This equality is the famous Euler's theorem. Euler's formula. Super important. Super important. Why it is so important? Because you will see 1 minute. Allow me 1 minute to finish this. And then we can close this after the 1 minute. As theta equals to 0 degree. Okay, we have case number 1. Okay. So r times e to the j 0 equals r times cosine 0 is 0, this is 1 is R, so no big deal. When theta is 0, no big deal. Okay? What about if theta equals pi? What happened? And for simplicity, and we let R be 1. Just for simplicity, we let R be 1. Okay? So the left-hand side has this E times J times pi. Right? We let R be 1, theta be pi. So the left-hand side is simply E to the J times pi. Okay? What about the right-hand side? We have 1 times cosine of pi plus J times sine of pi. Cosine of pi equals what? Come on. Cosine of pi. What is cosine of pi? Cosine of pi? Minus 1, negative 1. Good. Sine of pi? 0. Good. So e to the j pi equals negative 1. Or let me bring negative 1 to the left side. I have e to the j pi plus 1 equals 0. Wow. What a surprise. If you look at this equality, what do you see? You see the natural number, E. You see the unit imaginary number, J. Okay, this guy. Okay, E is equal to right? You see the natural number. You see the unit imaginary number. You see the pi, you see the unit number 1, real unit number 1. You see the number 0. So this equality combines all the magic numbers in mathematics. Okay? So this equality is called what? The king of equalities or equations. Looks very simple, but it combines all the magic numbers you can see in one equation, in one equality. So that's why it is so special. It is so special. Okay? Got it? All right. I think time's up. I have to stop here because everyone's hungry, including myself. Right? Okay. Before you leave, can I give you a simple assignment? If you look at the lecture note in the section 0.7, I attached lots of the method code. Actually, it's coming from the textbook, the latest edition, third edition. Okay, so I put them here. I need you to run the code. Okay, there are 6 or 5 programs. Very simple. Okay. Oh, 8, 9. Okay, up to 8, that'll be fine. Please run the program by yourself. Up to this guy, 0.8. And homework 0. Number 0. Okay, run the code. What's the section again? Whatever, okay? Point 9 up to point 8. In the method code. So I need you to copy the code and put it into your MATLAB script file and run the code, see what happens. So basically, what you have to do is just copy and paste and run the program. But occasionally, you have to make some corrections, okay, due to the transform from the script file, from this PDF file to your script file. Sometimes some mistakes may happen. Okay, so you have to make a correction if that happens. Okay, run the 8 simple. That's very simple. Run the 8 code and see what happens. Okay, you don't have to hand in a code. If you don't hand in a code, that means what? You are free whether you want to do it or not. But again, because we are going to use the MATLAB a lot later on in this class, so it is highly recommended that you have to run the code in some sense. Okay? All right, let me stop here. Any question before you leave? Question? Okay, see you next week. Hopefully I can still see you. I can still see you. Okay?